Hi, I'm Shailene Pokris, and I'm going to walk you through the third grade CS launch module called Programming Patterns. As always, we start with a real-world scenario. Three friends are discussing having a birthday party at an arcade, and they begin to talk about how they would like to make their own games. And this gives the kids a motivation to want to solve the problem of how could I make something like this on a tablet. We found that with all ages really, but especially with younger children, that being able to make something that's personal, that the student creates and then can show to others, is very empowering and gets them quite excited about computer science. The first activity is called Story Factory, and I'll be switching to show you a few more pieces of how it all fits together, but essentially what you'll be doing is having the classroom break up into groups, and we call them function groups. So then each small group of students has a function to perform in the factory, and then the main group will assemble the story. So let me show you what that some of what that looks like here. So there are two different ways you can view the students can view what they're supposed to do in their group. So if this is the main group, first they have to do this little envelope setup. When it's time to start, for example, the main program group, they have a step in their flowchart that says it's time to start. We're going to say go, and then they follow the arrows, making decisions where necessary. After it gets to point number 2, it says, is there an envelope in the main program's inbox? Yes or no. And so this shows them the branching logic and the flow of control in a program. If for some reason these flowcharts don't seem to be working for your students, you can switch to the text-based version of these instructions. So I will show you that as well. Okay, so this is a document that's available in the LMS that you can access, and the students can also access it, so you can have them looking at these instructions through Canvas, or you can print them, whatever works for you. So this is the same program we just looked at. It's how to set up the envelopes to get ready to do the Story Factory, and it's just written out in a different way. You still see that branching logic, yes or no. If it's yes, do this. If it's no, do that. And then once everything is set up, the main Story Factory program starts running the factory, where it sends out envelopes to the function groups, and these envelopes are sent back with the type of word that the Story Factory needs, and then the story gets reassembled or gets assembled by the main group. So each of the function groups follows that, and then there are two messengers who run envelopes back and forth. And this is all explained in detail in your teacher notes. So the idea behind Story Factory is to get kids to think about how code can be modularized, and not just when you're writing programs, but solving any kind of a problem or setting up any kind of a system. That it's good to find a solution to one part of the problem and then reuse that piece wherever necessary. Okay, and just as with all of our activities, this has an introduction and conclusion questions for the students to answer in their launch log. The next activity is Rosie's Path, and this will be familiar to any of you who did the pilot program for kindergarten through second, except that we now use the circles differently. Now we have Rosie moving along a path instead of across a grid, and she has a few more commands that she understands. Rosie can follow functions, conditionals, as well as repeat loops. So repeat loops were in second grade, but now in third grade we've got new things called conditionals, or also known as if, the if folder, which lets them ask a question. If Rosie is standing on blue, do these cards, otherwise skip over this part. Or if Rosie has reached her doghouse, do this. If Rosie has not reached her doghouse, do this other thing. So the cards you see on this slide, it says function, spin once. What's going on there is that the students would put those 4 cards inside that folder. That's called a function folder. And whenever they want Rosie to spin in her program, they just need one card that says call function spin once, and then Rosie will spin. And they only have to define the function one time. So you will have to do some prep for this, including getting the card sets ready to go. And if you need more cards, that's okay. You can get them from the file section. But there should be enough there for 30 students at a time. So unless you want to make smaller groups, in which case you might need more cards. We also allow you to print small versions of the board game if you want to let students do desktop or tabletop version, or if it helps them to plan out their program to be able to look at a smaller version of the board. And you will have to prep the repeat function and if folders. They just need to be folded in half and taped closed. So to facilitate this, definitely read through the teacher notes, because these paths require a little more thought for setting up. The order of the colors will matter based on the challenge that you're giving the students. And we give you several challenges in the materials, so you can just follow those. And then if the students want to keep playing, maybe they can make up a path, or you can make up more for them. We do recommend that the teacher act as Rosie, at least for the first few times through, because that way the kids can see how it all works, and we know that Rosie will do exactly what the cards say and not try to interpret what the programmers might have meant, but instead follow exactly what their cards say. A little bit later on, if the students want to take turns being Rosie, that's okay. That's really up to you. Remind students about pair programming. We are going to continue to say this throughout all of computer science, throughout the entire pathway, actually, of Project Lead the Way. We think there should be well-established rules for how students collaborate when they are working together on writing a program. The third activity is called Code Sketches, and this is where you get to jump into hopscotch. So in the LMS, the students have access to, and you have access to, Part 1 and Part 2 Introduction to Hopscotch videos. And those are a nice little walkthrough that helps you to see how the interface works, how to get a new character, how to go in and out of the blocks area, how to play your program, things like that. So definitely take the time to watch those 2 videos. They're not very long. And then you can dive right into this activity. So in Activity 3, the students will learn about how to draw things on the screen and then think about patterns and how to repeat a pattern to make a bigger design. So let's go through Activity 3, Code Sketches. It's broken down into 4 parts. First, students learn to draw a basic square, then to repeat some code, then to create functions, and then they get some chance to build something unique at the end. Now keep in mind that the students will have gone through the hopscotch tutorials, the videos that show them how to get started with hopscotch. And throughout this procedure, the students are asked to write in their launch log. Now, right up front here, we say, we bring up the word algorithm. And the important thing for students to learn about algorithm is that an algorithm is a plan or a recipe for accomplishing a task. It really can be that simple. In computer science, algorithms often end up looking a little bit like code, like programming code. And let me give you an example. So in Rosie's path, the activity before this one, the students will see this document and be able to use this example from Rosie about what is pseudocode. Pseudocode is when you write words that are kind of like code, but it's not exactly the way you would put it if you were typing it into a computer, and it is easier for humans to read, yet it captures the logic and the stepwise nature of the computer program. So when you're writing algorithms, a nice way to write them is in something that is like pseudocode. The good news about pseudocode is there's really no right or wrong way to do it. You can make up your own system. So this would be a nice type of pseudocode for writing a Rosie's path algorithm. And if there's a path full of red and purple and yellow dots, given a certain set of constraints, this program would get Rosie to her doghouse. So this whole thing here would repeat until Rosie gets to her doghouse. And as you can see, it would go through each time she's on a dot. The program will ask, is this a red dot? If so, move forward. If this is a purple dot, then I need to move forward and spin once, because this particular challenge said that Rosie always has to spin when she's on a purple. And then this particular challenge said that Rosie has to jump over yellow spots. So she checks each spot before she decides what to do. So this is a pretty simple example, but it's a pretty powerful one because there's a lot of logic in there and not very many lines. And it's written in English so that people can understand it. This, just incidentally, this is also called a repeat until loop. Students will be familiar with repeat a certain number of times, repeat 2, repeat 4. Now there's also repeat until, and the until goes until this condition is met. So we ask them to write an algorithm for drawing a square, and then go into Hopscotch and pick a character and program it to write the square. So it's really well step-by-step spelled out for the students. This is the student-facing document that I'm showing you. And as you can see, the student guide gives them the background info on how to draw a square, that the inside angles of a square are 90 degrees. Even if students have never heard that, they need this little math lesson so that they know what to put into the turn block here, turn 90 degrees. All right, and this is really fun because just from those few steps now, you see the little octopus there has drawn a square, and it's a quick win for the students. They see that they've given their character a command and it has followed, and so it's a much quicker feedback loop than they had with Rosie's runtime. And we're always encouraging them, making them think about patterns and repetition and how to do things efficiently. So right away we're asking them if you see any patterns and could you replace them with a loop. We refer back to Rosie's path here, which is hopefully reinforcing some of those lessons that they learned there. Okay, now on part 3 we get into functions. Now this is also referring back to Rosie's path, because they've used functions in Rosie's path to complete the challenges that had said things like spin right or spin left or dance, that hopefully they accomplished those with the function folder cards. And now they're going to do that here with Hopscotch. So we give them an example of what you might do in a day, and then say, you know, you could take each of the things you do each day, and each of those could be considered a function. So, you know, travel to school has many more steps in it than just travel to school. And getting ready for bed has more steps in it than just those few words. You may need to go upstairs, you may need to brush your teeth, read a book, turn off the light. So those would be the steps of the function. So after establishing that connection for the students, we introduce them to abilities in Hopscotch. So Hopscotch calls its functions abilities because this programming environment is very character-based. And if you think about what the characters can do, when you give them a behavior that you're going to specify like this, that you want to be able to call call anytime you want, it actually does make sense to call it an ability. But the computer science term for this is a function. So here are two functions, two abilities. One is called wiggle, and it just makes the character move back and forth 10 degrees, twisting 10 times. And then this one, draw triangle, should be no surprise that it says repeat 3 times, and that this time the turn is 120 degrees. So the students are asked to use those, and after plugging in those blocks, see what it does on the screen. Okay, now they're going to create their own function for drawing a square. So you see we started with them making a square with just basic step-by-step. Then we showed them how a loop could help make the code shorter. And now we're showing how you can store that into an ability to modularize it down into just a single function call later on in your program. Okay, so here's how they define the function. And lastly, they get to be a little creative, change colors, do something with their draw square function that will create a neat pattern on the screen, a neat drawing. And some kids may go really crazy with this and have their screen completely covered in different colors, and that's fine. If you have any students who are not getting very creative, you might want to give them a few suggestions. So here are some examples. Now keep in mind this document is available to the students, so they will see these examples, and they will have to, if they want to recreate one of these, they will have to look closely to see what this program probably was made up of. So for example, the one in the upper left is a big square, and clearly the square has been drawn multiple times, so it kind of ends up looking like a snowflake or a star. The one in the upper right is just a circle of squares, and even after drawing that, the students could go back and maybe have another circle inside, or change the distance that the character walks for the edges of the square. So say that was draw 100, it could leave a trail for 100 steps. You could change it to 25 steps or 300 steps and see how big or small your pattern gets. The triangle ones are really neat too. So hopefully you'll have time to let them really just play around with this. It's similar to spirograph or what they might do in art class, and it can really get them thinking about angles and combining shapes and wonderful things like that. And so we always have conclusion questions, and we always have a launch log activity in every launch log request in every activity. So that about sums up activity 3. This will be a learning curve for the students. They will probably not have had hopscotch before, so your challenge as the teacher here is to just facilitate, make sure they're doing pair programming, that everyone's getting a turn to work on the iPad, and that they're thinking about solving the problems together. Hopefully seeing that collaborating tends to get you to the solution faster than working by yourself. All right, so after doing the 2 unplugged activities and then the Code Sketches hopscotch activity, the students are ready to embark on a project using hopscotch. They are going to use the grid, which is laid out in an XY coordinate system, and make an interactive program. So this Project 4 student-facing document may seem a little lengthy, but that's because we need to give the kids some background information about the grid and how to work within it, how to specify locations and read locations and things like that. So they can walk through this. There are a lot of good images that you may choose to project on the board as a reminder, or even walk through this with them. Yeah, so the resolution here is not great, but you have a copy of this document to look at. So we're first off just telling them the origin x equals 0, y equals 0 is down here at this red dot, and then how to find out where this girl, her name is Chalana, where she's standing, and that her coordinates are 660 and 510. So that's the position she's at. So this is a little bit of a lesson right at the beginning of this project, and then we get right into how to do something that interacts with the user. Creating projects on the iPad is wonderful because they are already very interactive devices. You know, they respond to tilting, they can you can touch the screen, and it's something that students are used to interacting with. So to be able to, for them to be able to program something that responds to those kinds of inputs is pretty exciting for them. So we go right into some of the cool things that Hopscotch and the iPad allow you to do, which is things like tilting or shaking or tapping a character on the screen. And we are going to have them respond to those actions by the user. Okay, so here's a little chart to help them plan, and then they quickly will come to the realization that it would be helpful to be able to keep track of values that might need to change over time or that they just want to record. So a variable is like a bucket or a placeholder that can hold a piece of information, and then you can call that piece of information by the name of the variable. You can also change the value of what's in that bucket. All right, so we talk them through that, and we explain that in Hopscotch there are iPad values as well as values for each character. The iPad values are basically what other programming languages would call global variables. They are available to every character in the program. So we're going to have the students make use of that by putting a few things in the iPad values. One being to keep track of a number of lives. All right, so they can actually set this up how they like. We're recommending 3 lives for the game, and then they're going to learn how to reduce the number of lives as the game goes on, depending on how the user's doing, and also how to use a timer. And we give them a lot of hints here. The teacher document gives you a lot more insight into how they can solve these things. So for example, here is the code for setting up a timer. It decreases by 1 second every second. And if you start with 30, it will take 1 away and then loop back around, take 1 away, loop back around, take 1 away until you get down to 0. We give you a couple of warnings here. If the students are checking for the let's see, hopefully you can see this. Let me make it a little wider. I know it's probably a little hard to see, but you can also just open the PDF. What we're showing you here is that it could seem intuitive if they want to end the game when the character's lives get down to 0. They could just say when lives equals 0, but that won't work because the value of lives when the program first starts is going to be 0. It defaults to 0. So until you've assigned the number 3 to the number of lives, the program will think the number of lives is 0, and so won't ever actually run. It'll just end right away. So instead, we give you, the teacher can see this. The students, we hope, are going to figure this out and get it working on their own. This is a similar kind of warning about the timer. You don't want to say when the timer equals 0. You want to check if. Use the check once if. All right, and then it's time for the Creative Arcade problem. This is just like all of Project Lead the Way launch modules. This is the student problem, and they have to work in groups to solve it, and we don't give them a whole lot of help. We give hints and we make it very clear what the problem is. Let me go to this document. But we really expect the student to be able to come up with answers on their own. And they may struggle a bit, and that's okay. All right, so here is the introduction. They get to make their own game at last, and we really drive home the engineering design process here. It's very important, and it's a continuing theme all the way through Project Lead the Way, that there is a process that you go through when you're building something to solve a problem. So that's what we walk them through here after, yes, of course, another reminder about pair programming, and then giving them the design requirements. We're asking that they have a game with at least 2 characters. At least one of the characters should be controlled by the user, meaning the player, the person holding the iPad. They can control that character by tilting, tapping, shaking. They could even have 2 players competing against each other, in which case 2 students would be touching the iPad. We require that they keep a score and that they keep some kind of a count that will make the game end. So either when a certain score gets reached, or when a certain number of lives are used up, or just a timer, like how many points can you get in 3 minutes or something like that. So they may have to use the timer that they just learned in Project 4. And so you will probably find yourself referring back to Activity 3 and Project 4, because that is where the students got a lot of the content that they're going to need to put together to build this. They have all the building blocks. They know how to do a timer. They know how to set a number of lives in decrement. They know how to detect collisions between 2 characters, and they know how to draw designs. So they just need to be creative in coming up with what they want their game to do, and then how to make it happen. So these are the steps, and they should be using their launch logs quite a bit at this point. They'll need to do some brainstorming, making a list of ideas for games, and then really thinking further about whether that's a realistic kind of a game, and would that actually work, and would it be fun, and does it actually meet all the criteria. So remind them about pseudocode, about writing down their algorithm, drawing flowcharts or pictures, or even jotting down phrases with some arrows showing what happens first, what happens second. Things like that are all meant to be done in their launch log, and that's pretty free form. If they would like to use the graph paper for drawing images, or if they just want to use it as note paper to write words, that's fine. Okay, the model step is the 3rd step in the engineering design process. This is where they actually build the thing. And so the reminder here is about the pseudocode, and also tells them you are going to really build it in hopscotch. If you planned it well in your launch log, you should be able to go from that to getting your hopscotch program coded. I have a feeling the students will spend the bulk of the time on the problem working with the blocks in hopscotch. They will try something, it either won't work at all, or it won't work the way they expected, or it'll work just fine, but then they realize they want to make it do something a little different, or a little bit better. So there should be a lot of back and forth between the hopscotch stage, the play, when they're playing their project, and then back into the characters blocks. We do ask them to document what they built, and then to evaluate. Go back, make sure that your solution actually does what it needed to do, and then also do a little bit of user testing, usability, and also getting feedback from peers. Please remind the students that it is absolutely okay to make mistakes. It's expected in engineering, especially computer science, where you may think that you have a working algorithm, you get it all programmed, and then realize you put some things out of order, or forgot a variable, or had a plus sign where you needed a minus sign. There are all different kinds of revisions that happen, iteration. And that's actually good and healthy and a normal part of programming, and the more comfortable they can get with that, sort of unknown and sometimes frustrating feeling of, oh, when are we going to get this to work, or why didn't just, I wish it would just work. Eventually, when they get more comfortable with it, and they've done it a lot of times, they'll appreciate that process because it helps to refine the end result and make it even better. Students should be able to talk about and write about what they did. And so we asked them to write down what their solution was, and maybe even a little bit about what they might change if they had time. The conclusion questions are, it's up to you if you want to also discuss them in class. We encourage students to answer these in their launch logs. You may choose to have the students talk with each other as well. When everything is finished, the students should complete the check for understanding, and that will help them and you to assess their understanding, and also to reinforce. Just going through the check for understanding can reinforce their knowledge and skills. I do want to remind you and encourage you that this is a pilot, and we really need your feedback. Please post any questions whatsoever to the discussions area on the Launch Pilot PLC in the PLTW LMS, and participate in those discussions. We will answer you. We will also be holding office hours, let you know when those are going to be, and ask that you let us know if you're going to come to that, and possibly even send us the questions that you're going to have. It's okay if you just show up to see what others are asking or talking about, but if you have something you've been struggling with or a question about, feel free to post it to the discussion board or email it to Juliana, and then we can be sure to address it in the office hours. All right, that's it for Grade 3 programming patterns. Have fun.